I am back, and I'm here to practice some complex number arithmetic. So I'm going to share my screen, just like that. And then I'm going to open this file here using the general software. Maximize it. Now, we have to do these operations with complex numbers. So what is a complex number? Well, a complex number looks like this. That's just an example of a complex number. 5 plus 3i. They always have a real part and an imaginary part. So there's the general form, a plus bi. And of course, these can be negatives. So you could have like -7, and they can be decimals. That's fine. But what is the I all about? I is the imaginary unit, and it represents the square root of -1. 1 times 1 is 1, and -1 times -1 is also 1. So there's no number which, when you square it, gives you -1. However, we can imagine that such a number exists and works and solves that problem for us, and we'll call it I. And then we get a very interesting arithmetic as a result. We call these numbers complex numbers. They have a real part and an imaginary part here. Okay, so even if you didn't know anything about complex numbers, you could probably do some algebra with them because of how they were set up in the first place. Like, for example, here, this is just simply 7i. And here, this is 7 add 6i, 4i, -15i. Very simple. It's as if it's really just algebra, but with the letter I. Now here, it's tempting to say -9i, take 5, right? But follow convention. Put the real number first, and then put the imaginary number next after it. So write down -5, take 9i. Likewise here, this is 15 add I. And here, we have to expand the negative sign. So let's see if I can do it in my head. -3, add 5 is 2, 6i, add 3i, take 8i is just I. There, like that. And for this one, 11 take 7 is 4. 3i take 2i is just I. Now we get into actually using the property of I itself. And we have to go a little bit beyond just plain old algebra. So, for example, if you just expanded this out and you wrote -8i take 32i squared, technically, that's correct. But you're expected to replace I squared with -1, like that, and then realize that this is -32 times -1, which is +32. And so you correct it and write 32, take 8i, just like that. This here, I'm a fan of this symbol. It's called the interpunct. And it means multiplication. So it's really just asking, what is 5i times -i? So that would be negative 5i squared, and I squared is negative 1, so that would be negative 5 times negative 1, which is positive 5. Down here, we've got negative 10 I cubed. Now, let's think about the powers of I. Powers of the imaginary unit. I to the 1 is just I. I squared by definition is negative 1. I cubed will be negative 1 times I, so negative I. And then I to the 4, well, that's going to be negative 1 times negative 1, which is positive 1. And then it'll go around in a loop. It'll repeat itself. So I to the 5, to the 6, 7, and 8 will be I, negative 1, negative I, 1. Just there like that. Okay. So over here then, making use of that, this will be negative 10 times negative I, which is 10i. And over here, we've got negative 20 times I squared, so 20. You see, two imaginary numbers and a completely real number as a result. Looks like we can use FOIL here to expand the pair of double brackets, right? So we'll just run through it. First, outside, inside, last. That's what it stands for. Negative 2 times 4 is negative 8. And the outside and the inside refers to this. So we've got negative 2i, take 4i, and then negative I times I. Well, that would be negative 1 times negative 1, so plus 1. Just there like that. Then clean this up, and we get negative 7, take 6i, and that's all fine. Same story over here. And you can speed it up by recognizing that the F and the L in FOIL will form the real part, and the O and the I will form the imaginary part. So, negative 56 plus 18 is negative 38, and that's the real part. 21, add 48, which is 69. So 69i is the imaginary part. Here, we best multiply 7i by 3i to begin with. And when we do that, we get negative 21. So negative 21, and in the brackets, negative 8, take 6i. And then just multiply throughout. So negative 21 times negative 8 is negative, or is rather positive 168. And negative 21 times negative 6i is going to be positive 126i. Here, same story. We'll get the real part first. 16, add 5, 21. And the imaginary part next. Negative 20, add 4, so negative 16i. And it's done. Real part first. Negative 12, add 16, so 4, beg your pardon, that's not right. Negative 12, add 16 is 4. That's fine. Imaginary part next. So 24 add 8 is 32. And here. $34 add 12i. Next, 8 take 6i all times, -4 take 4i. Real part first. -32 add 24, -32 take 24 rather, is -56. Then 24 take 32 is -8i. There, like that. Okay, and here's something interesting. We're squaring a complex number. So you could write out the complex number twice and do FOIL. But let's think about it more generally. Whenever you get patterns, you want to look for them, or the possibility of patterns. Okay, so the real part is going to be a squared take b squared. Because I times I is -1, so there. And the imaginary part is going to be 2ab. There, that's the general form. So if I apply that pattern here, it's going to be 1 squared, and then we have -7, that's serving as b right now. -7 squared is 49, so 1 take 49, which is -48. And then for the imaginary part, 1 times -7, but the double of that, so -14, and stick an I right there. So that's fine. For this one here, probably better to do 6 and figure out the product of the pair of complex numbers and then multiply that by 6. So let's do that. So we have 28 take 12, which is 16, and the imaginary part is -24 minus 14, which is -38, and then times all of that by 6. So we're going to have 96. Take away 228i, just there like that. 3 complex numbers multiplied together. What to do? Some fancy algorithm? No. Just go from left to right. That's all. So I'll write -2 minus 2i like that. Figure out the product of the last two here. So the real part is -28, add 24, which is -4. And the imaginary part is -21, take 32, which is -53i, there, just like that. And now to figure out this product. The real part is 8 at 106, it seems. It's rather 8 take 106, which is -98. And the imaginary part is 106 add 8, which is 114. So 114i. Now here, we're going to have 35i cubed. But we remember that I cubed is just -i. So it becomes -35i. Likewise here, the cube of 6, 216, and then the cube of I, which is -i, So stick a minus sign there and put an I right there. Now, what about this one? 6 times -4. Just remember that this is a product here. Okay, 6 times -4. That would be -24. So -24 and then times I squared. Well, that would be +24. And then plus 8, which is 32. As for over here, we just distribute the -6. So we're going to have -24 plus 36i. And here we're squaring a complex number. We could rely on the pattern from earlier. So let's do it. 64 take 9 is 55. And then 2ab, so that's like 8 times -3, and then times that by 2, so -48, right? And then just I there like that. Here, the real part is -1. The imaginary part is 4i. We figure out this product here, and then expand and figure out this bracket here. So, -18i squared. But I squared is -1, so this becomes 18. And then -3 times -7, so 21. -3 times 6i, so -18i. So, all in all, it's 39 take 18i. Here, figure out the product first. Right, -6i. Open your brackets. Real part first. -64. Take 48. So, -112. Imaginary part next. So, -64. Add 48. Which is 16. -16. -16i. And so now just expand that -6i right there. We know that this will turn that part real, the last part real, and the first part imaginary. So we'll do it in that order. So -6 times -16 is +96. Times by the I squared is -96. There, like that. -6 times -112 is 672. So 672i. Now, how are the following problems different? 2 at x all times, 3 take 2x. Versus 2 at I all times, 3 take 2i. Well, they're different because this one will result in 3 terms that you can't simplify, whereas this one will result in, ultimately, a 2-term expression known as a complex number. We can actually compute that, though, and prove it. So, but this one here, it's written in a non-standard order, but that's no problem at all. When we expand it, we get -2x squared. And then here, 3x take 4x. That would be -x. And then lastly, 6. You cannot reduce that any further. Just replacing everything with I, like that. I can see why someone might think that they're the same. But here you are obliged to recognize that I squared is -1, so this becomes -2 times -1, which is 2. And then 2 add 6 is 8. So it becomes 8 take I. As for this problem over here, well, let's see. It would be 2 add x, take 3, so 1 right there, and then x plus 2x, so 3x there, like that. And here, 2 take 3, so beg your pardon, that is -1 there, and -1 there. And then I add 2i, so that's 3i. So they're not so different, really. Okay, so that was finished. That is finished now. We'll just save it and move on to something else, namely properties of complex numbers. What's that all about? Finding the absolute value of a complex number. What does that mean? That means trying to reduce it down to just a single number. Okay, let me put it this way. 1 add I, you can sort of, I want to say the word imagine, but maybe it's not the best idea. You can visualize going 1 along the real axis, which I should do in red. 1 along the real axis, and then 1 along the imaginary axis. And so the overall size of that complex number, like its distance from the origin, which is just good old 0, is the square root of 2. It's kind of trying to capture this idea that like 1 add I is the same size as 1 take I. But without further ado, let's try it out. It appears to be the repeated application of the Pythagorean theorem. So this, for example, is the square root of 7 squared at -1 at the square root of -1, which is 49 at 1, which is square root of 50. But then you have to try and simplify this third. We know that this is root 2 times root 25, so 5 root 2. And that's great. This here is a similar story. This is root 50, so 5 root 2 as well. And let's check and see if that's correct. And it is. Wonderful. So we'll proceed forward. So in my mind, I just sort of block out the plus and minus signs because they don't really matter when you're squaring. And so I just instantly turn them into squares. So I see that 2 and it triggers a 4. I see that 4 and it triggers a 16. I add them together and I get a 20. And then I square root that 20. And I know that it's just 2 times the square root of 5. Likewise here, 9 at 36 is 45, so that's 3 root 5. 100 add 4 is 104, which is 2 times the square root of 26. 16 at 64 is 80, which is 4 times root 5. This is the 3, 4, 5 triangle, is it not? So we just say 5. 64 add 9 is 73, which is a prime. 1 add 64 is 65, which is 5 13s, which cannot be simplified. 16 add 10 is 116, which is 4 times 29. So 2 root 29. And now we must graph each number in the complex plane. -3 add 4i. So we go -3 along the real axis and +4 along the imaginary axis. And there you have it. That's the complex number in the complex plane. Otherwise, and this is sometimes called an Argand diagram, after some French mathematician who I will learn the name of. Actually, why not learn the name of him now? Okay. We type in Argand on Wikipedia. Okay, we're not getting results. Oh, there he is. This person here. A Genevan amateur mathematician. All right, Genevan. In 1806, while managing a bookstore in Paris, he published the idea of a geometrical interpretation of complex numbers. Wonderful. Okay, continuing. -1 add 5i, that's just going to be here. -1 take 4i, down there. 4 add 4i, right there. Let's make sure that we're doing this right. We don't have to do arrows, do we? No, apparently not. That's fine. -3 add 5i. 2 add 4i. And now identify each complex number that has been graphed on the complex plane. Well, that would be -5 take 4i. That's 2 add 4i. This one here is 1 add 3i. 1 take 5i. And finally, or penultimately rather, this is 4 add 2i. And then comes -1 add 5i. Okay. All sorted, all handled. Great. Let's now move on to this skill. Rationalizing imaginary denominators. Really, this is talking about complex number division. Like dividing 2 by 8i. That's really what it's talking about. This number here is wholly real, and this number here is wholly imaginary, or I've heard it be phrased as purely real, purely imaginary. But nonetheless, I regard them both as complex numbers. It just so happens in this case, the imaginary part is 0. In this case, the real part is 0. So how do we actually do this? We multiply by 1. 1? But won't that leave it unchanged? We multiply by a fancy version of 1. Perhaps you've seen this trick before. We multiply by I over I. And the result of me doing this will be 2i on the top. And what on the bottom? 8i squared. Well, I squared is -1, so -8. There, just like that. And then this here should be negative a quarter I. So 2 divided by 8I is negative a quarter I. Let's check that that's right. Brilliant. Or negative I over 4. That's another way to do it. Great. So following the exact same pattern, basically, this will be negative 3 over 5I. What about this one here? Well, this, we cancel out the negatives 5 first, negative 5s first. So this is really 1 over I. And then timesing the top and the bottom by I, we get I over negative 1, so negative I. Isn't that interesting? 1 divided by I equals negative I. Okay, here. That's 1 over 9I. So I over negative 9, I over negative 9, which is negative I over 9. 3 over negative 2I. So 3I over negative 2I squared. So 3I over 2. I on the top, I on the bottom. So 6I, take 8 over negative 9, just there like that. And then go through it. So we have negative 2/3 of I. We should put the real part first. Okay, 8 over 9, take 2 over 3I. Now, what to do for this one? We'll times the top and the bottom by I as usual. So we have 4I, and then negative 9I squared, so that's positive 9. And then negative 6I squared, so that's going to be positive 6. So that's 9 over 6, which is 3 over 2. And 2 over 3. Quite pleasant. And here, times the top and the bottom by I once more. Or we can exploit this pattern over here if you want. Okay, times the top and the bottom by I. All right, negative 3I, take 10, all over negative 6I squared, so 6. Then that becomes negative 10 over 6, which is negative 5 over 3. And then take 3 over 6I, so take a half of I, and we're done. Brilliant. Top and the bottom, times them by I. We'll have negative I, take 8, and then we have negative I times I, which is the negative of negative 1, so 1. And there you go. Negative 8, take I. Next up, top and bottom, multiply them both by I. So we'll have 10I plus 10. All divided by 5. So that makes 2 at 2I. Here, what do we do? Times in the top and the bottom by I won't work because that's not going to get rid of the imaginary parts down here. What we need is a new trick. We times the top and the bottom by what's known as the conjugate. The conjugate. of the number, of the imaginary, of the complex number rather. So for a add bi, the conjugate is a take bi. If a complex number is denoted as z, as it typically is, then the conjugate is typically denoted as z with an over bar, a bar on the top. Sometimes I've seen it as z with a little star there like that. Sometimes. And yes, you can do it to the top here, like that. It's seen as a legitimate operation symbol. Okay. So let's see how that plays out. Put brackets on the denominator. Make the conjugates. So -2 plus 6i. That needs to be on the top as well. Otherwise, you're not multiplying by 1. So let's get the bottom first, because my claim is that this turns the bottom purely real. Let's do it. And where does my claim come from? My claim comes from the fact that you can see that doing the O and the I in FOIL, that would be -2 times 6i and -2 times -6i. Putting them together, we get 0. So the O and the I cancel out. So we need only worry about the F and the L, the first and the last. So -2 times -2, which is 4. And then -6i times +6i, which is -36i squared, which is -36 times -1, which is 36. Just there like that. So 40 down in the denominator. As for the numerator, be sensible. Do 5i times 6i first to get the real part. So we're going to have 30i squared, which is -30. Then 5i times -2, so -10i. And when we simplify, we get -3/4, -1/4i, just like that. It's a simple trick, really. Very useful. Here we'll have -1 take 3i. And on the top, exactly the same. And so expand out on the bottom. So we have 1 plus 9, so 10. And on the top, -8i, take 24, so plus 24, like that. And then you can sort it out. So 2.4, take 0. I'm not sure why this is being slow. Take 0.8i, there like that. Did you notice the size of the conjugate? Here we have 40, here we have 10. Interesting. Well, the size of the product of a complex number and its conjugates. Let's see why that is. Let's generalize. So we're going to do a add bi multiplied by a take bi. We know that the middle two terms cancel out, so we only concentrate on f and l, so a squared. Take b squared times I squared, so plus b squared. Just there like that. So, given that knowledge, this one here, problem 13, we can instantly see that it's 64 at 25, which is 89. So we just write 89 on the bottom. And on the top, we're going to multiply it by the conjugate of this, so it's negative 8 plus 5i. How lovely. This one here, down in the denominator, that's 4 at 64, which is 68. And on the top, we have to multiply the conjugate of this by I. So, what will that give us? So that's negative 2 plus 8i times by all of that multiplied by I. So 8i times I is negative 8. Negative 2 times I is negative 2i. So it should be there like that. So it should be negative 4. Negative 4 over 34, so that's negative 2 over 17. And this should be negative 1 over 34 times by I. Great. Here, the denominator's magnitude will just be 9, 36. Add them together, you get 45. Then do 4 times it by the conjugate in your mind. The conjugate is negative 3 at 6i. So 4 times negative 3 is negative 12. 4 times 24i is 96. And then see if you can simplify. So we notice that 3 seems to be in common everywhere. So negative 4 over 15 plus 32 over 15 I. There like that. 36 is 72. So 72 down here like that. But make sure that you're doing it right. Don't just keep marching on in case you're making some mistakes. So problem 15, we have negative 4 over 15 at 32 over 15i. That's for problem 15. And that's right. No, it's not. No, it's not. Uh-oh. Strange. Negative 4 plus 8. I'm making a mistake. Well, you have to correct yourself. Okay. Oh, goodness me. 4 times 20. Goodness me. What a blunder. 4 times 6 is 24. What was I doing? So that should be 8 when you divide it by 3 properly. I'm only human. Okay, here we go. 72 on the denominator. Got to be careful now. And what's on the top? This has almost thrown me off completely. No, it hasn't. Negative 10 take 5i. And negative 6 take 6i. Just there like that. We'll sort it out. Just push on ahead. Negative 10 times 6, that's 60. And then 60 add 30i squared. So 60 take 30. So that's 30. And then 60i add 30i. So that's 90i. And all of that is divided by 72. So what happens? Well, we get 10 over 24, so 5 over 12. $30 over 24, so 15 over 12. So 15 over 12, that's just 5 over 4. Did I recover 5 over 12 at 5 over 4i? Great, I did. No problem at all. Okay. Here, the denominator will be 81 at 64, which is 145. The numerator will be negative 5 take 9i, all times 9 take 8i, and we have to figure it out. So 145 down here. Figure out the real part first. So negative 45, sorry, minus 45 take 72. Minus 45 minus 72 is minus 117. And then the imaginary part, 40, take 81, so minus 41. And that will do. Here, denominator, 25, simple, 9 and 16, 25. Numerator, okay, I believe that's fine. Next, denominator, numerator. Okay. Okay. Yeah, I believe that that works. That's all good. We'll save that and we'll wrap up. 45 minutes, it appears. That's sufficient. All good.